Hello everyone, I'm Dr. Jim Daly and today we're doing another training session and we're talking about folate metabolism. Now this is something that's a really key system in the body. It has a lot of implications for many health conditions and you really want to pay attention because some of this is kind of difficult material, to be honest. I had trouble with this in biochemistry. It was hard. And I know a lot of people who still have trouble with it who've taken the classes and studied it. So it's a little bit difficult area, and I apologize for that. And I don't anticipate that most people are going to really retain all of it, but there are some important points that I hope you will retain, and this will give you a kind of understanding of how folate metabolism works and how it's important for your body and why you might want to consider one kind over another kind. With that, let's move on. When we're talking about folate metabolism, we're really talking about how the body uses carbon. Now, most living organisms are primarily made of carbon, and if you look at our little pie chart down here, you'll see that by dry weight, get rid of the water, we're basically about 80% carbon people are. So, it should be obvious that carbon and handling carbon in the body is something that's really important. Looking at carbon another way, you can see on this little chart that when we're not dry weight but wet weight, we're about 63% of the atoms in our body are hydrogen. Now, hydrogen's a little tiny atom, so by weight it would be much less. Oxygen is 25.5% of the number of atoms in our body. Carbon makes up about 9.5%, and the rest, all the other atoms together, is only about 1.35% of the atoms. That's nitrogen, which is really quite important in the body, as also considers iron, calcium, all these things make up a fairly small percentage of the body. Now, they are very important, don't get me wrong, but they don't make up the percentage of the body that carbon does by even close. Now, your body has to go through some jump some hoops, so to speak, to get that carbon where it needs to be in the body. So some very major systems in the body are basically designed to handle carbon. And some of you have seen some other lectures I've done on some of this, so this may be somewhat familiar. But if you look at this slide and look at that yellow dot circle there, that's a carbon, it's a methyl group actually, a carbon with 3 hydrogens. Now, methyl's metabolism is how most of the carbon in your body gets moved around. It's these little methyl groups. And that's what S-adenosylmethionine does. A lot of you have heard of SAMe. Well, that's what this is. That's what S-adenosylmethionine is. And SAMe basically transports and donates these methyl groups or carbons to different molecules to make your body able to use them to make things. They're used for the biosynthesis of many substances in the body. Absolutely required for life. You can't, if this system completely broke down, you'd die. SAMe is a high energy molecule. So the energy molecule itself can drive many of these reactions. Liver is where the most SAMe is made and used. And we're talking about today how the body takes that small yellow highlighted molecule and uses it to make it available in the body. Now, first of all, that the carbon has to come from somewhere, and we get it from foods as well as the substances that are used to use the carbon and make it utilized. The key nutrient for using these carbons is folic acid or folate. Folic acid itself is usually mostly found in either supplements or fortified foods. It's a synthetic material, vitamin, although it's sort of what you would call almost bioidentical to what you find in the body, and we'll talk about the difference in a little bit. Folic acid is very well absorbed in the body. It's easy to take up. However, folate from foods, the natural ones, are often much more difficult to absorb because they're bound in complexes that is hard to separate in the intestinal tract. So the folate is actually fairly difficult to absorb in most cases. Folic acid has been used very successfully as a supplement and as a food fortification ingredient to prevent neural tube defects. In fact, if you know Jonathan Wright, and probably many people listening to this will know who Jonathan Wright is. He's a very prominent medical doctor in the natural healing field, has a clinic in Tahoma, Washington, the Tahoma Clinic in Tacoma, Washington. They calls it the Tahoma Clinic, I think. Very well versed, has been in the natural healing arena for many, many years. And I remember listening to him give a talk, back in the early 1980s. And one of the things he said that really stuck out in my mind was the way he got involved in natural healing was that he had a child born with spina bifida. It's a very, very devastating condition. It's one of the neural tube defects. And at the time, most people, including most doctors, did not really know what caused that. And so he started looking up the research and found that most of those neural tube defects, it was already known, could be prevented by folic acid and folate. But nobody was telling people that women who are pregnant at that time need to take folic acid. Now it's very common. Any doctor will recommend that women who are pregnant or have the possibility of becoming pregnant, that they use folic acid and take supplements, a prenatal supplement with folic acid. But back then that wasn't the case. And he went from amazed to really angry that this information was available and he didn't know it as a medical doctor even. And that people weren't being told this information that was in the scientific literature already. And as a consequence, he had a child with a severe birth defect. Fortunately, that's not the case. Folic acid, and there are detractors to folic acid, and we'll talk about that. However, folic acid has prevented thousands and thousands of neural tube defects. They've been shown in country after country that when they start fortifying foods with it, the neural tube defects decline in the country. That's in epidemiological studies. They also know that if they give supplements of folic acid, much, much less likely to be neurotube defects in the newborns. So that's a really important point to make. First of all, folic acid does have benefits, and it is something that, we still sell folic acid. We sell methylfolate also, but we still sell folic acid because if you need something inexpensive, folic acid is quite cheap, and it works pretty well. It's not the best, but the methylfolate is quite a bit more expensive. So I'll just put that out right at the front. Now, deficiency of folate is a common cause of a lot of things, and of course, the impaired methyl metabolism, because that's what it does. Deficiency of vitamin B12 is also a common cause of impaired methyl metabolism or carbon metabolism. Other vitamin deficiency also cause it, but to a lesser extent. Niacin, riboflavin, vitamin B6 can all, if it's really low in your body, it can cause those same kind of methyl metabolism problems. Also, genetic differences in the enzymes along the pathway can result in an inability to have optimal folate and methyl metabolism. So there's a number of things we have to be careful about. Now, folate deficiency can have a lot of consequences, and when you consider that we're 80% carbon, and this is the system for utilizing carbon in the body, it makes sense that it would affect a lot of different things. Of course, neural tube defects we've already mentioned. Diagnostic criteria for folate deficiency is a megablastic anemia that you can actually see under a microscope if you look at the red blood cells. Elevated homocysteine, that appears earlier than the megablastic anemia, but it's elevated homocysteine is an indicator that something's not right with this methyl metabolism. Impaired production of platelets in the blood, fatigue, low energy, premature gray hair. As you get more serious, mouth sores and tongue swelling, and growth problems. These are all well-established deficiency diseases and symptoms. Suspected deficiency diseases and symptoms include such things as depression, irritability, persistent fatigue, lethargy, pale skin, tender tongue. Some of these overlap a little bit. Irritability, diarrhea. So if your husband or wife is irritable, just tell them they need some more methylfolate, and they'll get the hint. But anyway. But that's kind of like us here. We don't like to use bad language, so if we think somebody is shooting a line, not telling us the truth, we tell them that we don't tell them that they're full of something. We tell them that they need to take Vegelax. So, that they're Vegelax deficiency, and that's our laxative formula. So you get the message. But anyway, as we go, going on with our current topic, I'm sorry about that. Causes of folate deficiency. Well, there's a lot of causes of it. Junk food diets are low in folate almost always. So that's a big one there. But also just poor diet in general. People with Crohn's disease and celiac disease often have trouble with absorbing folate. There's some certain drugs and oral contraceptives that are linked to folate deficiency. Alcohol impairs folate absorption, and there's defects of the folate cycle itself. Now, let's look at single carbon metabolism for a little bit. I used this slide I changed it a little bit, but just about the same, I think about 2 years ago when I was talking about vitamin B12 and folate. But let's just start down here on the bottom right-hand corner and just up a little bit where you see folic acid. Folic acid has to be converted to folate, tetrahydrofolate actually, to be used. And there's an enzyme that does that, dihydrofolate reductase. And we'll look at that a little bit more closely. And you can see the arrow going over to folate. Okay, well, the tetrahydrofolate is bound to a methyl group over here. And I left some of this out to simplify it. So then you get methylfolate that goes over um, to the left-hand side. So folate sources are taurine, amino acids, choline, betaine, MSM. A lot of these things can be sources of the methyl groups to make methylfolate. And you can see the number of nutritional products are involved. We need niacin in there, B6, riboflavin, and an enzyme called, I hope I get this right, 5,10-methylene tetrahydrofolate reductase. That's a mouthful, but I got it right, MTHFR. So that's an enzyme that's involved in this process. And like I say, I left some steps out there, but you can see that folate, with going through all those steps there in the middle, comes over and becomes methylfolate. Okay, now methylfolate is holding on to that little CH3 that we saw earlier in the slides. And B12 helps to attach that to homocysteine. You can see the B12 just right there in the middle in red is going to transfer from the methylfolate, the methyl group, to methionine. Okay. Then only folate is left as the arrow goes on across. Well, methionine is then converted to S-adenosyl methionine. Straight above the methionine, you'll see S-adenosyl methionine. That's that SAMe that we were looking at right there at the very first. And that is a highly active molecule that transfers methyl groups to a lot of different things. And you can see it goes over, arrow going left from there, it becomes S-adenyl homocysteine. When the methyl's removed, it goes up to an unmethylated molecule. To the left, it becomes methylated. And that can be serotonin, it can be dopamine, melatonin, amino acids, creatine, L-carnitine, epigenetic methylation, all of these kind of things. And epigenetics, let me just explain what that is. That's one way that DNA is modified to make it be used correctly is to put methyl groups on the DNA that can either increase the expression of a gene or decrease the expression of a gene. So when that doesn't work right, your gene expression doesn't work right, and you can have a lot of problems as a result. But that's another lecture for another time. But just letting you know, and then that circles around to homocysteine, and it starts all over again. Actually, it turns out the folates, once they get in this cycle, they're used over and over and over, probably thousands of times a day in the body. This just keeps on going. So that's the only reason we get by with micrograms amounts of folate, is because it's used it's used over and over again and recycled continuously in the body. Now, you'll notice that I have two things highlighted in yellow down there, the DHFR, dihydrofolate reductase, going from folic acid to folate, tetrahydrofolate to be more precise, and MTHFR, the enzyme we mentioned a while ago, the 5,10-methylene tetrahydrofolate reductase. These are two genes where there can be a real bottleneck if they don't work right, and they often frequently don't, unfortunately, in this system, and can cause health problems. So we'll talk a little bit about those two enzymes later, but those two things are real bottlenecks for this whole system. Okay, well, let's talk about dihydrofolate reductase first. Now, this is the first one we said that was involved in the conversion of folic acid to tetrahydrofolic acid, which we can actually use. Now, folic acid actually does this, the DHFR actually does this in 2 steps. Takes folic acid and converts it to dihydrofolic acid. And you can see the dihydrofolic acid up there. And the 2, if you look at the very bottom, the 2 H's down there are what were missing in the folic acid and was put on there by the dihydrofolate reductase enzyme. Now, from there, the dihydrofolic acid goes again reacted on by DHFR and goes to the tetrahydrofolate, which is what your body's going to use in that cycle we just looked at. Now, the first step is quite slow in the body. So we end up with, a lot of times when we take that, with unreacted folic acid in the bloodstream because it doesn't get all converted. And if you listen to a lot of people on the internet and even some of the scientific literature about 15 years ago, there was a lot of concern about, is folic acid toxic because this unreacted folic acid builds up in the body. And there was a lot of concern about it. However, it appears that that was unfounded, and I want to make that point very strongly because we know from experience that folic acid does a lot of good things. And the concern about it being possibly toxic came from epidemiological research by a very good researcher, actually. But still, it was epidemiological where you see associations. And as people studied that more in the future, they began to realize, for one thing, that it didn't accumulate that much, the unreacted folic acid did. And remember, this is a water-soluble vitamin that your body can excrete. So, and secondly, even when it did, it didn't appear to be toxic, that people were being harmed by it. And a lot of the studies that were showing high levels of unreacted folic acid and being associated with premature dementia or other symptoms. I think, the reason for that, and you can't say it for sure, is that basically it wasn't because of the unreacted folic acid. It was because of people with genetic defects in the DHFR probably that were causing that high level of unreacted folic acid. And that was causing them to be deficient in the tetrahydrofolic acid and in the folic acid cycle. So it was something different that was happening, and that's something you have to watch with these association studies. It wasn't the unreacted folic acid causing the problem. It was because the enzyme here, DHFR, wasn't working correctly, and they were deficient in folic acid. At least that's my opinion. I can't quite prove that, but we can see a lot of evidence that unreacted folic acid is not toxic in the body, at least at the levels we normally see. Now, nobody can say for sure that if you have really, 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 really high levels of unreacted folic acid, maybe it could be toxic. We don't know. That hasn't been that well looked at. But we do know that under normal situations, people are not being poisoned by folic acid, although you will hear people say that on the internet. I really think that the evidence is strongly against that viewpoint. Okay, better keep moving. Now, 5,10-methylene tetrahydrofolic reductase is also a important enzyme in this whole thing. And what you look at here I can't quite show it to you, but on the left we have the first part when the tetrahydrofolate is first methylated. Actually, it's made into a ring. If you look on the left-hand molecule, you'll see a little area with a squiggly line. Okay, that's where we're looking at. Now that methyl, where that just to the left of that bend, of that squiggly line is a bend, and that's where a carbon would be. That's the methyl carbon that we're talking about, right there. And then you go to the right, you see on that same area, you see a CH3 standing up. So it's broken that bond where the squiggly line is, and suddenly you have a methyl group standing up. Okay, it's become available now. So that's what MTHFR does, is make that methyl group available. It's kind of like if I held this stick like this from both sides, it would be hard to get it loose from there. Now, turn loose of one side and it's up like that, you can grab it much more easily, right? Okay, that's what it's doing. It's making that carbon where it can be grabbed and put onto something else. And that's the purpose of this enzyme. This enzyme is the rate limiting, what we call the rate limiting enzyme for this whole cycle. So that's where, you know, it's really controlled. If this enzyme isn't working right, the whole cycle gets sluggish and declines. So this is what we call rate limiting enzyme for folate metabolism. Now, can this get out of whack? It absolutely can. MTHFR has genetic variances. So does DHFR, dihydrofolate reductase. It has genetic variants too. And actually they're fairly common. However, they don't seem to be quite as destructive as the MTHFR ones. But I suspect if you had variants that slowed down both systems, you'd be in big trouble. But genes that can have a slight differences in their structure that affect how well the proteins they encode function. And if you look at the DNA on the right, you see a kind of a green area that's indicating that there's something wrong there. Well, you see the two strands, and I think everybody knows that we get one set of genes from one parent and one set from the other, and they're not always identical. That's why we have differences in people, and there are not clones of one parent. But in some of these important enzymes, they should be the same from both parents a lot of times, but sometimes they're not. And sometimes getting one different variant will make a gene not work so well. However, and we call that, say they're heterozygous, like if we talk about heterosexuals, one, you know, they're both different, a man and a woman. However, if two of them get one of these bad variants, somebody gets both of the bad variants from the both parents, you know, then you've got a lot more serious. We call that homozygous because they have the same, like a, you know, homosexual, two of the same sexes. So we know that a lot of times the MTHFR genetic variances can affect how that gene works and how that protein works, the enzyme works. One common one is what they call a 677CC, which is our most common type. However, if you have a 677TT, you're homozygous for a variant that's less effective, basically. If you have a 67CT, you're heterozygous. That's not quite as bad. You can usually get by okay. But about 10% of the USA population is actually homozygous for that variant. So they really don't do the methyl metabolism, folate metabolism nearly as well as do the rest of the population. The people, if you have something as high as 10% that are homozygous, you're probably looking at, I don't really remember now, 40 or 50% of the population are heterozygous. They're probably just a little bit less effective, but they probably aren't affected too badly. And there are other variants too. The 1298C variant affects neurotransmitters, but not most of the folate cycle, and we don't quite understand why on that one, or at least I don't. But anyway, we can have variants in MTHFR that really affect this cycle that we're looking at. And so what do we do about that? Well, there's a lot of companies giving tests for that right now. And for people who have this genetic variant that puts their folate cycle at risk, they're really recommending pretty high doses of methylfolate because it bypasses that enzyme. That enzyme is the one that's used to make the methylfolate in that cycle. So that kind of bypasses and gets right, and you're giving the active enzyme form of folate that way. Not quite sure how well that works because the body makes so much of it, whether you get enough to help enough or not. That's something I've kind of questioned, really. How much do you really have to take to make it worthwhile to do that? But we don't know. But methylfolate we know is the more active form of folate or folic acid. Although, even though the folic acid is the oxidized form and is most often sold, but still has to be converted a lot. So if that gets held up and the MTHFR gets held up, then you're really getting into a mess with your folate metabolism. So methylfolate is much more available and as an active form of the vitamin than the folic acid is. That's not to say the folic acid is not beneficial, because it is. Now, daily methylfolate tablets are available to swallow or chew or take however you want to, but it's a really good high-quality folate. And they're made of non-animal ingredients. Now, homocysteine, a lot of the problems that we get come from homocysteine. And if you look, I'm going to go forward and back up here. If you go back to the folate cycle, you'll see homocysteine there. Remember that cycle where we made the methionine and then the acetyl methionine, the SAM, and it went over to do the methylation in our previous slide, and then homocysteine was left. Okay, homocysteine does a lot of nasty things if it builds up. The endoplasmic reticulum, stress, the glutamatergic, I'm suddenly tongue-tied here. Sorry, folks. Anyway, glutamine receptor activation, which is really important in the brain, but it can cause damage in the brain if you overactivate it. DNA damage and activation of these p53 genes, which actually causes the cells to die. So it can do a lot of nasty things, and particularly it's very bad for the heart and the brain. We know that elevated homocysteine is. But when we don't have the MTHFR working right, then the homocysteine starts building up because it doesn't get recycled very efficiently. So that's one thing that we know. When we're deficient in folate, if we're deficient in B12, homocysteine builds up because it can't be recycled, and the acetylmethionine is used up. So that ends up being a pretty serious complication. Well, back to this one, we know that homocysteine is a major mediator of folate and vitamin B12, or deficiencies, symptoms. Homocysteine is something the body continuously makes because it's going through that cycle all the time. But normally we recycle the homocysteine. It goes back to methionine, and then it's adenosyl methionine. But, you know, it only accumulates when this cycle isn't working right. Homocysteine has very damaging brain effects, as we just mentioned, and it actually, we can see that it causes brain atrophy. As we get older, we have some atrophy, but with homocysteine levels high, we have a lot more brain atrophy. And homocysteine is a well-known risk factor for Alzheimer's disease and dementia in general. Homocysteine may increase the permeability of the blood-brain barrier. However, most studies have not found supplements to be helpful as much as you would think, and that may be because the folic acid isn't getting converted as well. So that's a good argument for using the methylfolate, because almost all supplements in the past have been folic acid. The methylfolate supplements are fairly new, so I would guess the reason why they didn't find supplements that helpful, either they were too short-term studies to see the effects, or it was the folic acid not getting converted efficiently enough. And that's a well-known thing. But you can see the kind of brain loss that we see in dementia. It's very clear when you look at these pictures. There's some brain loss normal with aging. However, it can be greatly accelerated by disease or poor lifestyles, and especially diets low in folate and vitamin B12. Now, just to put single carbon metabolism in a nutshell, the major function of B12 and folate are to provide high energy carbon atoms for biosynthesis in the body. And that's biosynthesis of a lot of different things. And especially neurotransmitters seem to be affected very quick and early in the process. Both are common deficiencies in humans. Deficiency disturbs brain, heart, gut, and early development the most. Now, vegetarians tend to be pretty much okay for folate a lot of times if they eat a high-quality vegetarian diet. There again, the junk food diet where it's vegetarian or not vegetarian is usually not very good in folate, but vegetarians are often deficient in B12. However, almost anyone can be deficient in both, depending on their diet, their absorption, those enzymes, all of those things can, even with the best diet, if you have a genetic tendency not to handle it well, the DHFR variant that causes it not to work well, and even more important, MTHFR that we were talking about variant, that both are common in the population. Even with the best diet, if you have those variants, you're going to have a hard time doing this adequately, and it's going to cause problems. So, and supplements of both are probably the best way to obtain them in adequate amounts to be sure you're getting enough. And that's more true than probably for most nutrients. Even Victor Herbert, who was a very anti-supplement person, he's dead now, but years ago he wrote all these books about the supplement industry and putting them down. But he still told people to take B12 and folic acid. He said that was the exception. But I think he was wrong. I think there's a lot more good supplements. But he was a really left field anti-supplement person back in those days. But I kind of felt it was funny he did recommend those. The only ones that he would recommend, though. Nevertheless, I would like to point out that we have supplements with methylfolate in it and with the activated forms of B12 as well. our ageless brain is a really great formula. It has both methylcobalamin and methylfolate in pretty nice doses. That's something you really would like to be taking if you're worried about your brain down the road and dementia, because it doesn't, I'm not going to say it will keep you from getting dementia. There's a lot of factors involved in dementia, but B12 and folate deficiency are two causes that you do not have to neglect, and you can do something about those. So the ageless brain is nice in that regard. It's also in lower amounts in our vitamin B complex. We use activated forms of methylfolate now, and of vitamin B12, and a number of the other B vitamins. You can't compare this B12 with anything you'll buy in most stores, actually. It's just a really super product, our activated B12 is. And then we sell methylfolate by itself as well. So those three products right now are the sources. I can't think of any others that have methylfolate in them, but those are three very, very good supplements using methylfolate. And I think this is something that is so important. I really would, I take supplements with methylfolate every day. In fact, I take 2 supplements with methylfolate every day. It's something that I consider so important and so essential to a healthy lifestyle that I don't want to neglect that supplement, and I hope many of you will not either. And I hope I didn't go too far over your head. I know you're not going to pick up on all this. I struggle with it myself, some of these pathways and things, and I'm still scratching my head over some of the genetic variants and whether they have a big effect or a little effect. And there's like 24 different variants of the MTHFR gene. So, and how some of these variants affect or do not affect anything, we don't even know for sure. So there's a lot the scientists are struggling with in this area, so don't feel bad if you don't get it all. But I think it did point out today the importance of these enzymes and cofactors involved in methyl metabolism, and how you really need to maximize your ability to process carbon metabolism in your body. And that'll wrap it up for today. I hope you learned something, and I hope you'll join us again next month. And have a wonderful rest of the week. Goodbye.